Okay, another topic in simple regression is dealing with relationships between two a relationship between two variables that is not linear, as referred to as being curvilinear. And a good example of that is a study that was completed. And what it was the state of Florida um, looking at, I guess, a census of the alligator population. And what they would do is, and they can, from the air, from helicopters, they can locate alligators, and from the air, they can measure the length of the alligator. So what they wanted to do was to determine if they know the length of the alligator, can they estimate the weight of the alligator? And they wanted to run a test. So they ran a study, and for the study, they took images of alligators, and from the images, determined their estimate of the length of the alligator. And then they were able to, they physically located the alligator and then weighed the alligator. And they wanted to see, well, what is the relationship between the length of an alligator and the weight of an alligator? So in the study, if they were successful, they could, moving forward, use the results from the regression analysis and plug in the length of the alligator and running it through the regression equation, estimate what the weight of the alligator is. And in the image before you, you can see what you do see here is that the relationship between the length of the alligator and its weight does not follow, does not fit cleanly as a linear straight line. And what you would hope is that the data points would scatter along both sides of the line in a fairly random pattern. Okay, I'll live with the glitch. And we're not seeing that pattern. We're not seeing that random pattern of data points along the best fitting linear line. We can see that at the bottom part here, there's points where the weight of the alligator is underestimated according to the line, and here where the weight of the alligator is overestimated, and then at the tail end, the weight once again of the alligator is underestimated. And that's because the relationship between length and weight is not linear, it's curvilinear. So what we'll do is we're going to walk through some calculations to explore curvilinear relationships. So here we are. We have 25 alligators. The length of the alligators was measured, and the weight of the alligators was measured. So in terms of our best fitting line, I can put up the scatter plot. Oh, let's just do this, calculate our descriptives first. So I need my mean, my standard deviation, and I need my correlation. So equal to the average. Equal to the ST sample, or S. And I do that for both. And then carry it to 2 decimal places. And the correlation between length and weight is, using the Excel function, so I have a fairly solid correlation between the two. I can then calculate my slope, b, and I know that the slope is equal to the correlation coefficient multiplied by the standard deviation of the variable I'm trying to predict, which is y, which is weight, divided by the standard deviation of my x variable that I'm using to predict. And my y-intercept, which we for now call A, is equal to the mean of y minus the slope function multiplied by the mean of x. I'll confirm that. I'm going to put up the scatter plot. I'm going to insert a chart, scatter plot. My x variable is weight, or is length. Oh, my answer is always length. And my y variable is weight in pounds. Okay. Now I can confirm, because with the chart, I can add in my trend line equation. So I want a linear line, and I want to display the equation on. So there is my slope of 5.9024, and my y-intercept of minus 393.26. Okay. And I'll plug that up here. Okay. Now what I want to do is I want to look at my residuals. I want my predicted y. So my predicted weight, I'm going to plug in per alligator their length multiplied by the slope, and then I subtract or add the y-intercept, which is a minus value. So I go equals, let's do the y-intercept plus the slope multiplied by the length as recorded. That is my predicted weight for that alligator. It would help if I did my F4s properly. My dollar signs. It will help if I put the dollar sign for the right one. Sorry for the error. Oh, that's much better. Okay. Just make sure I'll check. Okay. The next thing I'm going to do is my residual. I'll do my residual, which is the actual y value, the actual weight of the alligator, minus the predicted weight, which is referred to as y hat. So the residual is the actual y minus y hat. And y hat, that symbol, which I'll pull here, okay. Stretch that out. So that's equal to the actual weight minus the predicted weight. Now I can throw in my scatter plot of my residuals with the x-axis the predicted weight, and I'll see a pattern to that. So what you see is my residuals have a pattern. And that is, I don't want to see that. I want my residuals. Here's the predicted weight right here, and here's the residual. My residuals, I have a positive residual for the lower values, and that's because I'm underestimating the weight. When I get into the middle of the distribution, I end up with negative residuals because I'm overestimating the predicted weight. I can see this is higher here. And then at the tail end, I'm once again underestimating my predicted weight underestimates the actual weight. So I have a problem. And as we can see in our slides, here is a nonlinear relationship in terms of my scatter plot, where in this case it's the opposite. I have positive residuals here, negative here, negative here. And then on the other side, for us, we actually have the flip for the nonlinear. So the nonlinear can go two ways, this way or the way that we've observed. Now, the best fit, if I can get a line that best fits, what I can do is I can I have a curvilinear exponential relationship. And that's the best fit here. So then what I need to do is I need to develop a regression model that allows me to model as not a linear relationship, but a nonlinear relationship, or curvilinear. As I can see here, my residuals, once again, show that pattern, and I don't want that. I want my residuals to be nicely spread out across the 0 point here with a nice random pattern of plus residuals and negative residuals, a band of them along here. Okay. You can go through a series of curvilinear transformations of the data or models, and I'm going to focus on the one that actually works. And the best fitting regression model here is with a quadratic. So what I need to do is I need to run a regression where I have two values for my independent variable, which in this case is length. The straight up value of the length and the squared value of the length. And I'm going to create now a second variable and run that through the regression model. So I got two values. So I'm now going to eliminate this, and I'm going to eliminate the predicted values here. I don't need this anymore because the linear regression doesn't work. And I'm also going to, for ease, I'm going to create, I'll explain why in a sec, I'm going to double up length. So length 1 is equal to that value there. And then length squared here. And that's equal to the length at 2. And then square it. I don't need this here anymore. So those are my values. So I've got two independent variables. I'll just gray those out. Okay. This is not a simple regression anymore. This is now a multiple regression because I've got two independent variables, length and length squared. Now, what you're going to need is you need the data analysis package for SPSS, or for Excel. So if you go to developer, Excel add-ins, this usually comes pretty standard with your package. make sure you have the analysis toolpack, and you can also add analysis toolpack VBA on here. So make sure that, so once again, you're in Developer, Excel add-ons, make sure you've clicked on Analysis toolpack, VBA. Then once you've done that, if you go to Data, you've got a data analysis package of tools. So we're going to use this to complete our regression, which will have 2 values. So data analysis, and I want to run a regression, and go OK. My input variable for Y is what I want to predict, and I'm going to have labels. So I'm going to click off labels, and I'm trying to predict weight. Now I'm going to be running a multiple regression, so my X variable has 2 components. Now the reason why I've duplicated length here is they need to be adjacent to each other for the multiple regression to run. So I have to make sure that they're actually, the 2 columns are beside each other. So I'll grab both columns. And now this is going to be a multiple regression. And I want my residuals, and I'm going to want the residual plots. Everyone got that okay? Okay, and then I go okay. Okay, so I got my residual plot here. This is the one I want. And as I can see here, this is exactly what I want. I want to have the pattern here. It's fairly random, right? I have a nice smattering across here of positive residuals and a nice smattering of negative residuals. There is no pattern to this. And I can also see the R squared for my model is 0.987. So I'm quite pleased to see that. And I can also, if I want, tap out the residuals. My coefficients here, length 1, the y-intercept is 410. Length 1, the coefficient for the time, or for the weight, is -11, and then for length squared is 0.0866. Now I can go back to my plot here, and I can confirm that with the trend analysis, the trend elements to with the trend lines. So I can more trend options, and what I want is I want linear. Let's display the I want to display the equation, and I want to display the R squared. Well, it's duplicated it. Okay, let's delete that. Okay, don't want that. Trend line, more trend options. I want linear, display the R square. And let's pull that down. So the R squared for the linear is 0.086. And I also want to add a polynomial. And I want to display the equation. There's my polynomial. Order 2 means that I have the value and then the value squared. Now if I've done this correctly, if I go over to my output from my regression, I'll just copy the coefficients over to make sure I've got everything right. And then a Control V. So here it is. There's my y-intercept of 410, the -11 for x, and the 0.866 for the squared function. And what I can see here is my R squared the R squared for the simple linear, which is wrong to do because I can see it doesn't fit very well, is 0.83. The R squared for the linear, for the quadratic, is R squared of 0.987. In Excel, you can actually fiddle with this. So I can do a third order if I wanted to. I can see the R squared is 0.9934. It's becoming more complicated because I've added a cubed component. And with the second order, it's 0.8987. So going by the R squared, I can see how it's a decent fit. Okay. So that's what I would do in this case, and that's the curvilinear regression. So just one final piece. Let's go. We'll do this in SPSS. So here is our SPSS data for our alligator length and weight. How I want to do this, my analysis in SPSS is analyze, regression, curve estimation. Dependent variable is weight, and it is dependent upon length. And I can pick the quadratic and the cubic and the linear. Those are the three I showed in Excel. And away we go. Here is our quadratic. That's the one we had in SPSS. You'll recognize the 410 minus 11 and 0.087. And the R squareds, 0.836, 0.987, cubic, 0.993. We're pretty good with the quadratic. We're at 0.987. We're not adding too much in terms of R squared, so I would probably stick with that. And back to our Excel. So I can go back here, and I can add a third order, so 0.987, 0.9934. So you can see how that replicates from SPSS. And that's the end.